it anymore, but I used to do sentiment analysis stuff in grad school. I used it a lot for that. It was great for that kind of stuff.
You should encourage your company to use it more.
I'm a little scared of using machine learning and financial data, but.
Hi, I'm Samrat Kulkarni, work for Bell Labs, telecommunications R&D. I'm here for the pizza and to learn something new. I'm getting into the data science field.
My name is Chai. So I'm learning data science by my own and not in Scikit-Learn and just here to learn what you're presenting.
Cool.
I am Mike. I do consumer analytics for Condé Nast, and my team dabbles a little bit in Python. We're mostly R shop, R and SAS. So just looking to learn more about it.
My name is Naeem Tyson. I am a research scientist in natural language processing at About.com. We use Scikit-Learn for feature extraction and very simple statistical modeling.
Baseline who are here.
Yeah, that's good.
Pick them up during the conversation.
Yeah.
Hello, my name is Alex. I'm using Scikit-Learn exclusively, and I've used it a lot to create several algorithms and models. I work for a medical company, medical and health company now, or startup. So I find it very good, and I'm here to interact with people.
Who have submitted bug report to Scikit-Learn before here?
Sorry, what?
Bug report. Bug.
Only two.
Me too. We need to work on that. We're New York City, smart people. Okay.
Yes.
So how many people we haven't covered yet? Let's do quick 10 seconds so we know who's there and who you want to talk to after the event. Whose turn now? Okay, you guys, Nico, your turn.
Yeah, sorry, what are you asking?
Everyone introduce yourself and whether you use Scikit-Learn before.
Yes, my name is Nick. I work next door at the New York Times with Colin here. And we use Scikit-Learn as like essentially the main engine on all our models because it's a nice bridge between kind of production languages and modeling languages.
Are you guys an R shop or Python shop?
Oh, Python.
We're a Python shop mostly. I mean, you can do whatever you want, but when it gets closer to production, it's good to have kind of common infrastructure. So we decided on Andreas here.
I'm Ritesh. I switched to Scikit-Learn recently from R, and I was very surprised how easy it is. And we use it for asset prediction, asset price prediction.
I'm Aaron Rank. I work at the Department of Education, and I use Scikit-Learn for doing clustering financial data of schools.
Yeah.
I'm Ariusu. I'm Chief Data Scientist at Mashable. I use Scikit-Learn for a variety of the machine learning tasks that we have.
My name is Alex.
All right.
Hello, I'm
10 more to go. 15 to go.
Okay. I'm Emanuele. I'm a CERN physicist, and I'm learning Scikit-Learn these days.
Hi, my name is Joseph. I'm coming from a biotechnology background. Python and machine learning in general.
I'm Julia Torresan. I'm a data scientist at Trumpet. I started to learn Scikit-Learn.
Hi, I'm David Stewerman. I work at I lead an R&D team at Project Florida here in New York, and I dabble in Python myself. My team uses Scikit-Learn a lot.
Hi, I'm Rob Bennett. I'm another nuclear physicist, and I work for this guy.
how to do Scikit-Learn on production. Have you done that?
Yeah, but it's not sure it's going to be a whole talk, but yeah. There's now all companies ship stuff for doing integration now, like H2O and Datto and AzureML. It's no, this is for recording.
And new to Scikit-Learn.
Hey, Adam Lopich, work for Sales Analytics with E Squared. Big fan of Scikit-Learn, looking to learn a lot more about ensemble techniques to match together many different models for high performance.
Hi, I'm Guillermo. I work with financial data, and
All
I
companies
use
ship
Scikit-Learn.
stuff for doing integration now.
What's going on?
That's me.
What?
That's me 20 seconds ago.
Oh my god. What's going on? Oh, I see. I'm doing live streaming, that's why.
Oh, I'm live streaming myself. That's great.
That's why. Guys, I post the live streaming link in the comment section of today's event. Feel free to retweet it so your friend in the world can join you. Sorry, it's live streaming 30 seconds behind.
All right. That's okay.
And I have a meetup for spreadsheets, and we do some VBA right here in this building. So if you go to meetup and you type in spreadsheets in New York City, I think I'm the only one right now.
Mike, I play with Scikit-Learn a little bit, but nothing serious.
Hi, I'm Will. I'm a data scientist at Shopkeep down the road in Soho. I use Scikit-Learn heavily in my last role for classification tasks. I just started this one a few weeks ago, but plan to use it pretty heavily too. All my side projects, mostly Scikit-Learn as well.
Hey, Roman, I do analytics at a telecommunication company. I do not use Scikit-Learn.
What? Just kidding. Just kidding.
I am Ravi Rao. I've done a lot of work in imaging, neuroimaging. I used MATLAB before. I'm just interested in learning a new processing pipeline.
Hi, my name is Emil. I'm getting a PhD in political science. I should be writing my dissertation, but I'm procrastinating right now. I've only dabbled in, Scikit-Learn. Seriously.
That's great. Did we miss anything? Anyone? Julian, I saw you. Julian is a lawyer, and he quit his lawyer career, joined the boot camp, and want to become a data scientist. You will be the most data savvy lawyer in the world. So, thank you for everyone. Thank you everyone for coming. I just want to give you a little background on what we do here. My meetup is called NYC Open Data. I started in May 2013. I initially volunteered to teach a lot, and after half a year, people asked me, can I pay you so you can teach me more? That's how I started my school, NYC Data Science Academy. And right now, we have a lot of great mentors, including today's speaker, and Owen, Joe, Max Kuhn, Ramnach, Igor. So if you're interested to become a data scientist, great place to go. And we place our candidate and great talent in the community. You can sign for the hiring at nycdatascience.com, or apply for a bootcamp, or come to our event. We have events very often. Usually, when not that busy, it's twice per week. That's why so far we already get 144 events in the past 18 months. I work very hard, so whatever you want to hear, tell me, I'm gonna make it happen. Like, I heard a great topic from today's introduction. I think next time we can host some event about how you can use Python on production environment. I know you're looking up. I know what you want, and I'm gonna make it happen. So let's welcome today's speaker, Andrew, to talk about the Scikit-Learn. And I told him make it as hard as possible, as challenging as possible, because it's New York City. We're smart people. One's dead. Okay.
So
I'm going to try and make it project over to you.
okay, yeah, I think we're trying to make the projector over there work so that everybody can see.
loading the app and seeing the content. Yeah. Which part? Yeah. So the idea with the helmet video is.
No?
It'll come up. You can do your thing. I'll come back in a second.
All right.
Yes, so it's intent-based for the front camera. So if you decide to take a photo,
So
that would be captured through the front.
does this work? And also, why is the other guy on?
What's going on? That you see in the display.
No, that's not here. It's. I think it's the other room.
Okay, try to speak louder so they don't hear them.
All right. Thanks everybody for coming. So yeah, Vivian told me to be as advanced as possible. So the slides are more like all the very complicated things you can do with Scikit-Learn, but I also want to go through all the introductory stuff maybe a bit more, as there are a couple of people who don't have that much background using Scikit-Learn at all. So yeah, I'm Andreas Mueller. I'm at the NYU Center for Data Science. I'm one of the core developers of Scikit-Learn. Just a little bit about myself. I did my PhD in the University of Bonn using structured prediction for image segmentation. I went to Amazon Machine Learning in Berlin, working on computer vision applications and time series forecasting. And I gotta go closer to the mic. All right. And now, since the end of last year, I'm at the NYU Center for Data Science, where we work on open source for data science. In particular, I basically now do Scikit-Learn full-time there, which is cool. So, as you probably know, Scikit-Learn is a Python library for doing machine learning. It includes a lot of algorithms for doing standard machine learning tasks like classification, regression, clustering, dimensionality reduction, manifold learning, together with a lot of tools to do parameter estimation, do model selection, pre-processing, and so on. And so I'm going to talk about how to do all this. Well, Scikit-Learn is a huge community effort. So this is the list of the, I think, like 36 people that are part of the GitHub organization. So that's the people that can merge your pull requests. There's at any time, there's 10 to 20 people really active of the core developers, but each release has about 100 to 200 people that contribute to the release. So we just released the 0.16 last Friday, and I think there were 163 people contributed to the release. So yeah, brief overview of my talk here. I want to start quickly with some basic concepts in Scikit-Learn. And then I want to mostly focus on model building and evaluation and how you can set hyperparameters. Then I want to talk a little bit about out-of-core learning, how to learn when your data doesn't fit into your memory. And then I want to talk very briefly at the end about stuff that is new in the release from last Friday. So most of machine learning that people do is supervised learning, I'd say. And to do a supervised machine learning task in Scikit-Learn, you start picking your model. Let's say you want to do a classification task, and you pick a random forest classifier. And the algorithm will be encapsulated in a class. And so instantiate your class, and you give it your training data, x-train, and your training labels y-train. In Scikit-Learn, we always call the data x and the labels y. And you call the fit function to create the model. And so the CLF object will now contain everything that's estimated from the data, so all the decision trees that were trained. X is always in Scikit-Learn NumPy array, that is number of samples times number of features. Y-train in this case would just be an array of labels for classification. Okay, so this fit stores your model in a CLF object, and if you get some new test data, you can call the predict function on some array x test, and will give you a prediction. You can also use the score function on this classifier object. This will give you the accuracy of applying the model on x test and compare it to y test. The other class of models that is most frequently used, I think, is what I want to call unsupervised transformations, like principal component analysis, PCA. So here you have some training data, and you estimate a model from your training data. You just call fit, this time without any labels, because it's an unsupervised algorithm. And this gives you a model of the principal components. So it stores what are the directions in the data that span the most variance. And then you can use this on some new data. Here I reduced my data to 3 components, and I can call transform on a new array x test, and will transform the data to the 3 principal three principal components of my training data set. And so the basic API is really for everything. There's estimator.fit to fit the model, always with X, but sometimes also with some supervised information Y. And then there's predict if you want to predict a new labeling, as in classification or in regression, or where you predict a target, or in clustering, where you want to predict for some algorithms what is the cluster membership of some new data. And there some algorithms have a transform, which is when you want to transform want to get a new view of your data, a new X, basically. Such as in pre-processing, if you want to scale your data, or if you want to do dimensionality reduction as in PCA, or if you want to do feature selection or feature extraction, then your model will have a transform method. And so these are basically the only three methods you really need to remember to use scikit-learn is fit, predict, and transform. And that's sort of the core API. And all of these basically always operate on NumPy arrays, except for some feature extraction. And things that you might want to do with your model is, for example, evaluate it using cross-validation, which is quite simple, using the cross-validation module, which in particular contains the cross-val score function. So the cross-val score function takes any model that you like. For example, here SVC stands for support vector classifier. It's just a kernelized support vector machine, libsvm. So it takes this model together with some data X, the true labels Y, and then some way to do cross-validation. Here I set CV equal to 5, which means 5-fold cross-validation. For classification, it actually does stratified cross-validation. And then this cross-val score runs the cross-validation for you, and print scores will just give you the cross-validation scores for the 5 splits. And as you can see, it does basically perfectly because I used Iris. So there's other ways to do cross-validation. There's a lot of classes in this cross-validation module that give you different ways to split the data. For example, one is shuffle split, where you give the number of samples in your data set, and then the test set size that you want, and the number of iterations. So what this does is it just randomly splits your data. Like in this example, split off 30% for a test set, and it does this randomly 10 times. And so this will give you 10 numbers. Sometimes this is, or sometimes people prefer this over like k-fold cross-validation, because you can independently tune how big your test set is from the number of iterations you do, and you might get a more robust estimate. So here basically I just created this class shuffle split, and instead of CV equal to a number, I give CV equal to this object that I created. Another one that's fairly popular is leave one label out. Here label doesn't refer to a class label as in classification. It's some external information. Let's say you're in a medical context where you have multiple patients and you have multiple data points per patient, and you want to know, can I generalize from one patient to another patient? So you don't want one patient to be both in a test and a training set. So here the labels would be, which patient does this data point belong to? And leave one label out would put one whole patient in a test set. That doesn't happen only in a medical context. For example, if you do work with websites and you have data from different websites, you might want to generalize across websites or across customers, or if there's any kind of grouping that you want to be robust to, you can use this to do cross-validation respecting these labels. So most algorithms in scikit-learn, as always in machine learning, have a lot of hyperparameters that you want to tune. So in scikit-learn, there's cross-validated grid search, which helps you tuning parameters. Particularly important if you want to use RBF kernel SVMs. So the grid search is implemented in the class that's called grid search CV in the grid search module. Before you do grid search, I would always advise to split off some test set to do final evaluation. So here I also get this train test split function and split my data. I think it is 25% in a test set and the rest for training. And I'll do training on the, I do grid search on the training part, and then I'll keep the test part for the end. To do grid search with scikit-learn, you need to define what are the parameters you want to search over. Here I have a radial basis function support vector machine, and I want to adjust the parameters C and gamma. So for that, I need to create a dictionary where the keys are the parameters, in this case C and gamma, and the values are the parameter. So the parameter values I want to search over. So I put in here, this is an exponential grid going from 0.001 to 100, both for C and gamma. then I can instantiate this grid search CV class with my classifier, the support vector machine, and this dictionary, this param grid. This grid search CV acts as what we like to call meta estimator. So this grid search CV now looks exactly like the support vector machine. It has fit, predict, and score. But what it does behind the scenes is a bit more complicated. So if you call fit on the training set, what it will do is it will try each possible combination of the C and gamma, do cross-validation for each combination, then pick the best value of the parameters. Then it'll use this value and train again, this time on the whole training set. Then it'll store this model, trained with the best parameter setting on the whole training set, and this is what it will be used for predict and score. So this is what's going on here behind the scenes, but you can just sort of call fit and predict. So this was the setting up to now was basically if you're training data and you have your training labels and you create the model and you want to adjust some parameters for your model. But usually it doesn't look like this. Usually there's the data that you get is quite different from the data that you want to feed your model. And there are steps in there like feature extraction, scaling, feature selection, and so on. And the mistake people often make is that they do cross-validation or parameter estimation just around the model. And they don't include the feature selection and scaling. The problem here is that if you do cross-validation here, the test part of your cross-validation was already used in the feature extraction and the scaling. So you're cheating, and your estimate of your generalization error will be very optimistic. So what you should actually be doing is do cross-validation over your whole feature extraction and everything pipeline. The way to do this in Scikit-Learn is with pipelines. And in the pipeline module, there's a function called make pipeline, which you can give basically a list of estimators, where the first ones are all ones that have a transform, and the last one can be anything. In this very simple example here, I use a standard scaler, which just mean removal and scaling to variance 1, and then a support vector machine. And so what this pipeline does is it will fit the first step, then call transform on the first step. The transformed data will be the one with mean removed and variance scaled to 1. And we'll pass this transformed version to the second step. This could, again, be a transformer, which would be fit on the data. Then the data would be transformed again, and so on, until it's passed to the last step, where it just calls fit.
Excuse me, you're saying that you will only scale on the split section, not the whole?
Sorry, here there's no cross-validation yet. Sorry? It's hard to? OK, I can use this. So here there is no cross-validation yet, but I'll come to this point in a second. So here, if I call fit here on the training data set, it'll fit the first one on the training part, transform the training part, fit the second one on the transformed version. If I call predict, it will call transform on the standard scalar, and then call predict on the second part. So the thing why I want to do this like this and not just write it by hand, basically, is now I can feed this into my grid search. So if I feed this into my grid search, the grid search does a splitting of the data in the cross-validation. And so both steps of the pipeline will see during fit only the training part of the split. So is that clear? OK, so because this pipeline acts as a single estimator now, and will see only the training part for training it and only the test part for testing it. And it works exactly the same way as with a support vector machine, only that we need to tell the grid search where it needs to adjust the parameters C and gamma. So here, the make pipeline gives names to all the steps, and the names are just the lowercase name of the class. So the support vector classifier is called SVC. And then there's a double underscore, which is sort of the syntax here. And then there's the parameter C and gamma. So apart from this SVC prefix, everything looks the same. But now you make sure that you only use your training part in estimating the mean. So for scaling your data, that might not be as important. But if you do feature selection, that is very important. So, and if you do feature selection, let's say you want to do a ANOVA test univariate feature selection, and you want to select the k-best features. and you want to find out which from 1, 2, 3, or 4 are the best features to select. Yeah, I guess this is again Iris. So what you can do now is you can search over this parameter jointly with the parameters of the classifier. So you can use the final score of the classifier to say what is the best parameter setting for my feature selection. So this will now search over all these possible combinations of the parameters. Okay. So I mean, this already lets you build sort of slightly complex pipelines, but they're all very linear. We can go even a bit more crazy and do what we call feature unions. Here, the idea is that you want to extract different kinds of features on the same data set. Let's say you have some pandas data frame and you want to extract different features from different columns. Or you have some text data and you want to extract features on the words, features on the characters, and also how many uppercase letters are there. And you want to feed the data into your pipeline, extract all these features, then concatenate these features and feed them to your classifier. And that is what feature union allows you to do. There's also in the pipeline module, there's this function called make union, and you just give it a set of transformers. Then these will be fit in parallel on the same data, and the result will just be concatenated. So here I use the example of, for some text data, the count vectorizer. I'll talk about this a little bit more later, but this is just feature extraction for text, once on the character level, once on the word level. And make union means I concatenate them together. And now I can call make pipeline out of these 2 feature extraction methods and a classifier. And so this text pipe is now a slightly complex object which extracts 2 kinds of features, and then there's a classification on it. And again, I can, for example, grid search the parameter C here. As I did before, I have to tell it, well, this is a linear SVC, is the name of this step here in the pipeline, and I can adjust this. What I can now also do is I can adjust the parameters of these feature extraction things. So let's say I want to look at how many characters do I look at in my feature extractions, or how many words do I want to look at, which is the n range parameter. And so if I want to adjust this, I have to, again, use this underscore notation, only there's now 2 levels of indirection. So in the pipeline, there's the first step, which is the feature union. And in this feature union, there's the first count vectorizer, which is count vectorizer 1, which is this one. And I want to adjust some parameter there. And in the feature union, there's also the second count vectorizer, and I want to adjust some parameter there. And then there's the linear SVC, in which I want to adjust the C. So I can tune all these parameters jointly here for all the feature extraction. So one issue with this, though, is if you add more and more processing steps, the complexity of searching over these parameters will grow exponentially, basically. And so you might not want to do this. One way to kind of deal with this, at least partially, is randomized parameter search, which I want to talk about next. So in randomized parameter search, instead of doing grid search, where you specify like a grid of parameters, let's think about the gamma and C for the support vector machine on the left. Instead of doing this, you just draw random samples for the parameters. So the idea here is that one parameter is important. Let's say this parameter is not important, but this one is important. And in green here, you see the function as a function of the important parameter, and in yellow as the function of the unimportant parameter. And if you sample on this regular grid, and you sampled 9 points, you did cross-validation 9 times for 9 different parameter settings. But you only really explored 3 settings of the important parameter. Whereas if you do a randomized layout and you randomly sample your parameters, you tried 9 different values of your important parameter. So this will give you a much, much better resolution on the parameters that are actually important. So for this to work, this only kind of makes sense, or mostly makes sense, if some parameters are important and others are not important. But that's often the case, but you don't know in advance which are the important parameters. So the thing that's great about this is, I think it's step size free for continuous parameters. So you don't need to say, I want to search my C parameter over these 5 different points. I just give it a range that I want to search over. Or usually I give it a distribution I want to search over. It also couples the runtime from the search space size. I can just say, I want to sample 100 points, and I can sample 100 more if I want. I don't have to tie this to how many parameters I actually want to adjust. And as I said, it's robust against irrelevant parameters. In grid search, if you add an irrelevant parameter, your runtime will increase by a factor of the parameters you try for the irrelevant parameter. For the randomized layout, it doesn't increase at all. So you can add as many irrelevant parameters as you like, which is great. Okay, so the way to do this in Scikit-Learn is basically exactly the same as grid search. So I use the same pipeline I used before, where I adjust some parameters of my feature extraction and of the support vector machine. But so the first two parameters are kind of discrete. So, but the last one, the C for the SVM, this is a continuous parameter. So instead of doing this list of these values from 0.001 to 100, this list of 6 values, what I do is I give it a distribution. So this is expon from SciPy stats. And this looks something like this. So this kind of mirrors this exponential grid that I gave it before. And what I can do then is do randomized search CV, give it the pipeline, give it the param distributions. And so that's exactly the same basically as with the grid search, only I have to also give it the number of iterations. And so if you have a lot of continuous variables, you should always use distributions for those. And only then does this give you a real benefit. I wouldn't use this for very low dimensional spaces where the grid search is very effective. And so in the future, we're going to work on doing Bayesian optimization like Spearmint or HyperOpt, if you heard of that. But actually, the randomized search is a very strong baseline for that. So it's very hard to beat. All right. Another way to deal with having a lot of parameters to adjust is generalized cross-validation path algorithms. And so I want to motivate this with an example of doing recursive feature elimination. In recursive feature elimination, you take a classifier, let's say logistic regression, you train it on your data set, and then you drop the feature that is least important, let's say the one that has the smallest absolute coefficient. Then you train it again, and you again drop the least important feature. And so you can reduce your feature set. So now let's say you want to adjust how many features you want to keep. And you could do this with Scikit-Learn using grid search. So what you're going to do here is, let's say, okay, for a parameter setting, that means we keep all features. We're going to train logistic regression, evaluate it. For the one where we drop one feature, we're going to train logistic regression, drop the least important feature, evaluate it. For the one where we drop 2 features, we're going to train logistic regression, drop 1 feature, drop a second feature, and evaluate it. So we're going to do the same work over and over again, because grid search 3 doesn't know that they depend on each other in an obvious way. So the way to do this is there's a specialized object in Scikit-Learn called RFECV, so recursive feature elimination cross-validation, which will drop all features like one by one, and then give you the best possible value using cross-validation. So this will exploit the structure of this feature elimination to do smarter parameter selection. And so I think it's kind of obvious how this benefits in this case, but there's also less obvious variants of this. Okay, so fit here will just give you the best parameter setting. For example, for linear models, there's a thing called path algorithms. Particular for Latho, this is pretty famous. Here you have on this plot the regularization parameter, and each of these curves shows you a coefficient of a linear model, how it evolves if you vary the regularization parameter. So, the thing is you can compute all of them very efficiently at once. So you start off with a very strong regularization, everything will be 0. Then you decrease the regularization, and you can compute what the coefficients will be like, and therefore also what your cross-validation score will be like for all values of the regularization path. And you can actually do this for not only for Lasso, but for a lot of linear models. It's implemented in Scikit-Learn. So in the newest version 0.16, we have this for logistic regression CV, but it's been there longer for Ridge classifier, Lars, ElasticNet, and so on. And so these will, in a similar way as this recursive feature elimination did, this will do cross-validation in a very efficient way to adjust the regularization parameter. So we also have this for feature selection. In particular, it would also be possible actually to do this for tree-based models, growing trees iteratively to different depth. But unfortunately, we haven't implemented that yet. But it's possible and holds hopefully also coming in the future. Slight caveat here is that if you use these together with grid search, so let's say you build a pipeline where you have some feature extraction or something, and then you have logistic regression CV, and then you want to do grid search over that. The grid search will do cross-validation, and then the CV object will do cross-validation again. And so you will have nested cross-validation, which you probably want to avoid. But we're going to fix that soon. OK. So that's everything I wanted to talk about with how to select parameters. Now, the thing is, all of these give you a number on which you evaluate which parameters are the best. And these numbers are giving scoring functions. So for this grid search, randomized search, cross-fault score, and the CV objects. And what they do is, by default, they use accuracy for classification or R² for regression. But this is not always optimal. In particular, I want to discuss this in the case where you have imbalanced data. So think about the case where you have 9-to-1 imbalanced data. So I think here I did a toy example of classifying the digit 7 against all the other digits. So one class is 9 times larger than the other class. And so I evaluate my support vector machine on this data set. And I get an accuracy of 90%. Is this a good classifier? No? Depends? Yeah, so I would claim that there's no way to know that. So if you do a dummy classifier that does the most frequent class, this is not a 7 class, it will also get 90% accuracy. So you could say, well, that's a pretty bad classifier. It has the same accuracy as the dummy classifier. But then you can look at other metrics. For example, a metric that I really like is area under the ROC curve. And this metric tells you this is a metric between, well, basically between 0.5 and 1. And it says this is basically a perfect classifier. It's close to 1. And this is the reason why I like this score much more than accuracy for imbalanced data sets. So what the score does, it computes the area under the ROC curve. The ROC curve is the false positive rate against the true positive rate. And what it does is it doesn't take the classification outcome of the classifier, but it takes its certainty score, so the distance to the hyperplane at the support vector machine, for example. And then it varies where to put a threshold to decide if it's a positive class or a negative class. You can see this as a ranking loss that it measures how often did you give something a higher score that was supposed to be negative, or how often did you put a negative example above a positive. And so if you use this score, then your classifier was basically perfect. But I also tried two different classifiers here, which are just support vector machine with different values of gamma, and they all have the same accuracy, but they have different levels of AOC. So one is the blue one, this is the default parameters, basically that's perfect. The green one is pretty bad, and the red one is just randomly. And they all have the same accuracy, so this is really a bad score here. One thing to keep in mind when using scoring functions like ROC AOC is that that really is invariant to the threshold. So we didn't do perfectly. It says we did perfectly, basically, but we only have accuracy of 90%. That means we did a bad job of picking this threshold and to say where is the positive class and where's the negative class. So that's something you need to keep in mind. So there's a lot of metrics available in Scikit-Learn, and you can just pick it, as you saw here, by providing a string to the scoring argument. So all the classes I talked about, all the functions, they all have the scoring argument, and you can just give it a string. And there's this scorers dictionary in the metrics module, and it tells you all the scores that you can use. There's also on the website. I think by now it grew a little bit. And the easiest way to use different scoring functions is just specify a string, because it knows whether to use the predict function or whether to use the decision function, or the log loss, for example, needs the classifier to predict the probability distribution. You can also define your own metric by defining just any callable that has as a signature an estimate that it was trained together with data and labels, at least for a supervised case. And so you should think about this as being the estimate that was already trained and the test data and the test labels. And then you can do anything and return any score. Higher should be better. And use this in your grid search or your cross-validation. And here, for example, I just used accuracy, but I penalized estimators that are very non-sparse. But you can come up with anything you like. Okay, so that was really all I wanted to say about model selection. And sort of the second thing I wanted to talk about is out-of-core learning. So what is out-of-core learning? That means learning when your data doesn't fit into RAM. I'll use it sort of synonymous with online learning, which is not really, well, but let's just say it's when your data doesn't fit into RAM. Scikit-Learn is mostly built about the data being in RAM as an NumPy array, but there's also some things you can do when it's not the case. Mostly I want to say don't do it. It's so much cheaper to just get a bigger machine. And really, so this is the EC2 machine. Just get a machine on the cloud. It's so much cheaper than a data scientist. So actually, I usually do this on my old laptop, which has 4 GB of RAM, which is 1 million data points with 1,000 dense features, which is, I would argue, already slightly big. You can also get like, an Amazon cloud machine. Amazon doesn't pay me anymore, by the way, but you just get one of these machines, and it has 86 million data points with 1,000 features dense. That's, I would argue, that's slightly large. So who really has more data than that? Okay, hands up, who has more than 256 GB of data usually? 1, 2, 3, 4, maybe 5 people, 6 people. Okay, so I don't deny this exists, but really for the majority of people, you should just get one of these. Or maybe you can even do your stuff on the laptop. Even at Amazon, I could often do things on just these machines. Anyhow, so for the 5 people in the room that actually have this kind of data, the rest is for you. So there's a couple of algorithms that support this. And in particular, there's this stochastic gradient descent classifier and some derivatives like the perceptron and SGD regressor and passive-aggressive regressor and classifier, all the naive Bayes algorithms, mini-batch k-means for clustering, incremental PCA for dimensionality reduction, mini-batch dictionary learning for dictionary learning. And so the way that this works is with the partial fit interface. So usually if you get your estimator and you call fit on it, and it'll forget anything it saw before. So if you can call fit on Iris, then you can call fit on MNIST, then call fit on ImageNet, and it'll not remember any of the previous data sets. But with the partial fit interface, it will remember what it saw before and try to improve. So here, this is just sort of doing stochastic gradient, and you give it more data to do more gradient descent. So what you have to do yourself with Scikit-Learn is basically you have to load the data from disk. This is what I do here. I do like, I imagine I have like 9 batches, and I load these batches from disk, and then give them one by one to this partial fit. And for the classifiers, I also have to tell it what are the classes that actually may occur in this data set. And so for the SGD classifier, you might want to go over the data multiple times, because it will only do like a single update on each batch, so you might want to iterate over your batches. The same goes for the k-means and mini-batch dictionary learning. For the naive Bayes classifiers, it's actually a closed form solution, so it's enough if you iterate over your data once. Okay, so, but this is basically all there is. You need to take care of creating the batches yourself, and then you can call partial fit. You should make the batches as big as possible to fit into RAM, because each time you call partial fit, there's some overhead it'll check that your data is okay and everything. So you should make the batches as big that they just fit into RAM. Okay, so the thing about this out-of-core or online learning is it's really hard to build pipelines because you don't see all your data. And so what I advocate is to make things easy is to use what I call stateless transformers, which are transformers that don't actually learn from the data. They're in Scikit-Learn, but they're not machine learning really. So you can use them without ever seeing the rest of your data. The simplest one is normalizer, which just normalizes each data point to unit length, which is kind of boring. Next one is hashing vectorizer, which I'll talk about in a second, and RBF sampler, which is kernel approximation. And yeah, so I want to talk about these a little bit more. So the hashing vectorizer is for doing out-of-core text learning, or text learning with very large data sets. And maybe for those who are not super familiar with working on text data, small reminder, standard way to represent text in machine learning is bag-of-word representation. That's kind of the simplest way to do it. It's implemented in Count Vectorizer or TF-IDF Vectorizer. and you start off with a data set of strings, like here. And so what you do is you first tokenize your data set using some regular expression and normalize it. So in Scikit-Learn, there's something very simple, just splits basically by white space and lower cases it. Then you have all these tokens for your one data point, but you can also collect all the tokens in your whole training set, and you build a vocabulary out of all your tokens. So let's say all the tokens were from Advac to Zisk. And then you imagine a large sparse matrix where you put in the counts for each of your data points, how often does each token appear. So most of them will be 0 because here our current string here only has 5 words, so there will be only 5 ones in there, and all the rest will be zeros. Then we use the sparse matrix encoding because we don't want to store all these zeros. That's the standard bag-of-word representation, but the problem here is that you need to store the whole vocabulary. So at least you need to go over the dataset once to start with this, and then you need to store the whole vocabulary. So what the hashing trick does is it gets rid of storing the vocabulary. And it's implemented in the hashing vectorizer. So it starts the same way with tokenizing the data, but then instead of using a lookup table, you just hash each of your tokens. So this hash function is something that takes in a string and gives out an integer number. So I give it each of these tokens, and I limit the integer number to be, let's say, smaller than 2 to the 10 or 2 to the 20 or something like that. And then this integer number will serve as an index into your sparse matrix. So I'll just say in my huge sparse matrix that is mostly zeros at point 832,412, I put a 1 in, that's for the u, because my hash of u is this number. So this way I never have to see the whole data set, and I can create a sparse matrix encoding one string by string. And so, yeah, that's how this looks in practice. So here I create an SGD classifier and a hashing vectorizer. Now I load batches of strings and put them in the hashing vectorizer. I just call transform. I get out the sparse matrix representation and then fit the SGD on that. So one downside of using the hashing is that you can't really go back. So if you learned a linear model like this, you can't go back and say, what does this coefficient mean? Because the hashing might have collisions, so multiple words might go to the same number. It's usually not a problem. I think there's papers about that. It's not a problem. So, but it means that you can't interpret your coefficients as easily. But with this, you can basically learn on arbitrary large text data sets, which is nice. So the next stateless transform I want to talk about are kernel approximations, which is, I think, my first contribution to Scikit-Learn, and actually maybe the only algorithm that I contributed, I'm not sure. So just a very quick reminder, the kernel trick. Okay. Who here knows what a kernel trick is? Okay. Very quick one. So you have your data. You want to classify the blue points versus the green points versus the red points, but you want to use a linear classifier and it doesn't work. So what you do is you can apply a feature function to your data and, for example, square your features, and then all of a sudden a linear classifier works in this expanded feature space. Then you realize that for training a linear classifier, you only need to know the inner products between your features, not the features themselves. And you think, hey, now I can make up all kinds of different functions that I call k, which is the kernel function, and don't have to think about what kind of features do they correspond to. And if I use a linear kernel, I'll just get the original data. If I use a polynomial kernel, I can do arbitrary long polynomial expansions without actually computing them. If I use an RBF kernel, I get possibly infinite dimensional features. That's great. And you can, but the problem here is that if you want to solve a kernelized SVM, it's sort of n to the number of samples cubed. Writing down the whole matrix, which you usually can avoid, is n to the square, is n squared, but sort of solving it is usually around n cubed. Whereas solving a linear SVM, for example, or just a linear classifier is more or less linear in the samples, at least Leombo 2 says so. So the problem, so if you have number of samples so large that you can't fit your stuff into RAM, and then you don't want something that is quadratic or cubic in the runtime. So what we do now is we just forget about everything that I just talked about, and we go back to feature maps. So this is what machine learning people did in the last 10 years. I don't know. They went to kernels, and they went back. And so the idea of the kernel approximation is that you construct an explicit feature map so that the inner product between these features is about the same as your kernel. And for example, for the exponential kernel, this is implemented in the REF sampler. This is also called random kitchen sinks. So basically, it constructs a feature map. You can choose how big it should be, but the scalar product of these features will be approximately the RBF kernel. So this allows you to do learn kernel SVMs with data that doesn't fit into RAM by using this explicit feature map. So you can use this RBF sampler. You have to give it the gamma for your RBF kernel. You have to tell it how many features it should construct. And then you can, so you have to actually fit it once so that it knows what the dimensionality of the data is. But then you can go through each batch, call transform, get your transformed features, and train the SGD classifier on it. So this will basically learn approximately a kernel SVM on data that doesn't fit into RAM. Okay, so now after I told you how to do this with Scikit-Learn, the hashing trick and learning kernel approximations, actually, if you're really serious about this, you might want to check out Vopal Webbit, because we are here at Microsoft. So John Langford has an awesome machine learning package for doing online learning and out-of-core learning. So we can do this with Scikit-Learn, but I think they can do it a little bit better maybe, or at least pretty fast too. So if you want to do out-of-core learning, you should also check out that. Anyhow, so in the last part of my talk, I want to talk about highlights from 0.16. So 0.16 was, we just released it on Friday or Saturday morning, something like that. And just very briefly, so what we added here is multinomial logistic regression, which is maybe surprising that we added this just now. Before we had logistic regression just from liblinear, which is super fast, but is one versus rest. And so it's a bit weird. We added logistic regression CV, which is this fast cross-validation to give you the best regularization parameter, incremental PCA to do out-of-core PCA, probability calibration for classifiers, which I want to talk about in a second, bridge clustering, which is also, you can do out-of-core clustering with that. It comes more from the data mining community, LSH forests for doing approximate nearest neighbors. It's supposed to be self-tuning locally semantic hashing. And and we also have more robust integration with pandas now, because we can now give pandas data frames to any estimator and it will not crash and burn, which is good. Also, pandas tends to give you NumPy arrays of D-type object with numbers in them, but it doesn't tell you that they are numbers. And so now we're more robust to that. Okay, but the last thing I want to talk about is probability calibration, which is what we just added. Basically, what it does is there's this calibrated classifier CV, which can turn either a classifier which doesn't have probability estimates, such as a support vector machine, into one that does have them. Or it takes one that has bad probability estimates, like a random forest classifier, and makes it into one that has good probability estimates. And by good, I mean calibrated. So what does calibration mean? It means that if I have an estimated classifier and tells me I'm 90% sure this is class 1, it should be correct 90% of the time. Otherwise, these 90% are meaningless. And so what this does is it uses cross-validation to train a classifier on a part of the data set and then calibrate the probability so that they actually reflect how well the classifier predicts. And this plot here, this is what's called a calibration plot. So for a given percentage that you pick, how many positive examples were actually predicted. So if you make a threshold at 50%, when a classifier says 50%, it's 50% certain, it should predict 50% positives. And so if you do logistic regression, it usually does a good job, which is the blue one here. If you do a support vector machine and try to run it through a sigmoid, it's a bad idea and you get a green curve. But if you use the calibrated classifier CV, then it works pretty well. So why should you care about probability estimates? One reason is if you actually make decisions that are, say, like money worth, and you know how much do you have to pay if you do false positive or false negative, you can use these probabilities and like decision theory to tell you what to do. Or maybe you're just doing a Kaggle competition with a log loss, then this will also help you because log loss needs probability distributions. Okay, that's all I want to say. Apart from our documentation is awesome, look at our documentation. It has everything I said and much, much more. Also, Center for Data Science is hiring, in particular hiring people like me, so that's a shameless plug. If you want to do open source for data science, machine learning, visualization, any data crunching, we just hire people to do open source full time. So if you like open source and you want to help scientists, talk to me. And that's there's if you're interested in what's new, there's a webcast with me and Olivier Grisel with O'Reilly on Thursday morning, if you're interested. But yeah, that's it. Thanks. Oh, questions?
Yeah, so GPU integration, I know that's something I read wasn't.
No, we're not going to do it. So we do.
Can you go into that a little bit more, though?
Yes.
I'm sure you get that question all the time.
Yes, so that's why it's in the FAQ. But, so basically our standpoint is it's too hard to build it reliably. We have people that say like, oh, this broke on Solaris with this and this version of GCC, and then we have to go in and fix it. So on Strata, actually, I said something like this, and then Travis Oliphant says, oh, that's so easy, just conda install. But that means that Scikit-Learn would rely on conda, and we don't want that. So you can install Scikit-Learn basically on any machine. Now it's pretty cross-platform, and we want to keep it that way, and we want to focus more on being cross-platform than on GPU support.
So if we want to do some like deep learning stuff, you just recommend using other tools for it.
Yeah, so we're gonna include some deep learning stuff for like if you want to get your feet wet, but if you want to be serious about it, use other tools. Also, you often want to specify like your actual architecture, and Scikit-Learn has more of a black box approach. It gives you an algorithm, doesn't give you a way to build an algorithm. So if you want to build, and in deep learning, you often want to build your own model. And there's good libraries out there maintained by very smart people that can do a much better job. Yes, we kicked out a hidden Markov model for two reasons. One is the API is kind of not compatible because it dealt with sequence learning, and basically everything in Scikit-Learn is matrix in, matrix out. So it's always number of samples times number of features, and having one thing in there that's have a sort of a different API makes it very awkward because it doesn't work together with the cross-validation, the grid search, and everything else. The other reason is that none of the core developers was working on it. And this means it had pretty low quality compared to the rest. So that, you need really one person that is sort of responsible and that will keep maintaining it so that it has a high quality standard. So if there's no one on a project who actually knows the code, who's actually using the code, you cannot really maintain it to a good state. And so we didn't really feel comfortable with the code because no one really knew it anymore. Those are the two reasons.
What kind of libraries would you suggest? What kind of libraries would you suggest for HMMs and neural nets?
Definitely not the same library. So if you want, for HMMs, it depends. If you want to do unsupervised stuff, there's HMM Learn, which is just a Scikit-Learn HMM that get kicked out. There's, if you want to do actually CRFs like supervised stuff, there's stuff called, do you want to do it for sequences is the question. There's a Scikit-Learn by Lars, which is fast. There's, for general structure prediction, there's my PyStruct. Also depends, do you want to do Python or not? For deep learning,
let's say Python.
Yeah, okay. Yeah. So probably Scikit-Learn, Seq-Learn. That's CRFs. For unsupervised HMMs, I don't know another one than HMM Learn. And for deep learning, depends on your level of abstraction, definitely Theano, and if that's too low level for you, then you can do PyLearn 2 maybe. There's also sklearn Theano, which is pretty new, but they wrap some existing models, and I think they're going to be interesting too. And obviously there's like Caffe and stuff, that's not Python. Anything else? No. Oh.
How does it lend itself to integration like MapReduce?
Well, the question is, how does this integrate with MapReduce? And I mean, depends. So this is like, it computes a model on a single machine using arbitrary many cores often, but on a single machine. So you can parallelize it arbitrarily for grid searches, for example. You can grid search a different set of parameters on any box. But you don't actually need MapReduce for that. You can do something much more simple because you just need to send like the parameter setting and then the thing will compute. You cannot actually do any parallelization over of the algorithm. Then again, if your data is smaller than 256 gigabyte of RAM, then you'll be faster doing it on a single core than trying to do MapReduce. Often. Let's say often.
Once you create a algorithm that you want to actually use in production, is there an easy or standard way to get all of the required parameters out? So for example, like if you train up a random forest to get all of the decision trees and everything out to, if it has to be implemented in like C# or something, whatever your production.
Well, if it has to be implemented in C#, maybe talk to the Microsoft people. They also have some random forests. Sebastian Novotny wrote them. They're pretty good. But I mean, if it's a linear model or it's an SVM, it's very easy to get it out. If it's decision trees, you have to write a lot of custom code to implement them. I mean, we thought about doing export to PMML or something, but it's kind of, there's people who wrote exporters to JSON for the random forests. But yeah, I mean, in the end, you have to implement your own stuff in C#, and it's going to be so much more work than the export part.
What's the compute cost for the calibrated classifier?
Well, it's the K in your cross-validation times the number of the underlying classifier. So if you do tenfold cross-validation, you're going to lose 1/10 of your data on average, and it's going to be 10 times as long. Also, I mean, because you're not using all of your data, it's not guaranteed to be better in the end in terms of log loss. Okay.
I would like to ask you about the problem I was contemplating maybe about online learning, meaning like learning in batch learning, and parameter optimization. I mean, what's your opinion? Like, how you do them both? Like the parameter optimization and online learning, or not?
You mean like at the same time, changing the hyperparameters while you're learning?
What would you do?
I mean, it depends. So for linear models, you could use warm starting, like change your regularization parameter. And things like changing the learning rate is like something people often do. But I don't know what kind of parameters you want to adjust. In a random forest, you're going to have problems, usually. But you can definitely, I mean, if you have a solution for one hyperparameter in a linear model, and you say, or like for one regularization parameter, and you want to learn for another one, it would be stupid to just throw away the one that you already learned.
Yeah, I mean, because I have a bunch of data, and then I optimize that, and then a new bunch comes with you, and it's like local optimize all the time, and examine one step another. I don't have any
I'm not sure if I understand your setting.
Yeah, I mean, I have batches of data coming, like 1 gigabyte per time, and I'm using like partial fit.
Yeah.
So can I use some kind of meta learning on top of that, like hyperparameter optimization on top of that, or not?
Not out of the box with Scikit-Learn. In general, yes, definitely. I mean, you could think about doing more online learning kind of things where you kind of, I mean, I'm not sure, do you want to minimize your regret over time? Then there's like a bunch of papers you can look up. But yeah, maybe you can talk about it offline. Okay.
No question?
Yeah.
Can beginners hang out by the coffee area afterwards for 10 minutes to try to figure out
Go ahead.
some of the stuff that happened?
Go ahead.
You can also ask me, I can hang out with you. So I was asked to give the hardest possible talk. And I said that at the beginning. There's also a version of this that is like, where there's like 90 slides, but the content stopped after the 5th slide here. So, but Vivian actually gave a more introductory talk like 2 months ago or 3 months, I don't know.
I recorded.
But yeah, but I can hang out at the coffee machine too, if you want.
Thank you so much. I have 4 quick announcements, and we're going to do a vote for tonight's talk.
Do I have to turn around?
Yes, later. First announcement is our bootcamp is graduating, and I welcome everyone to their job fair day. It's going to host it at Grand Central, our office. Everyone are working on their 5 projects. Some of them are really, really cool, like we're analyzing past authoritative turn-side data and try to figure out how you can solve the gem problem. And what authority directive team gonna stop by and see whether it's gonna trigger them to do something. I'm gonna host deep learning with R, how you can do deep learning with R, and also schedule like hack session with Andrew and see exactly how we can use the code in his life to improve your life.
Oh, there was a link. There's notebooks online that actually use this stuff if you want to try it out. On the meetup. Yeah.
So also we will schedule with you how we can use Python on production environment. If you guys have event space, welcome to talk to me. Our event is getting bigger and bigger. Especially if New York Times has space, we're happy to do that. If you're interested in bootcamp, I have a few flyers you can feel free to pick up. And thank you so much for Microsoft host us. Jim's in the back. Here are the Okay, we're gonna ask speaker to turn around, and we're gonna vote for him. Can you stand in here, in the middle? So if you really like his talk, awesome. If you think it's okay, this. If you don't want to see him again, to this. Okay, let's see. Please vote. I think you have so many hands in the air. Good job.
Oh, thanks.
I'm sending this to him. That's good. Thank you guys for coming.
I'm just going to plug this out.
I think it's copied already.
Yeah.
Two fast questions. One was the thing you had with the that was a contamination. If you normalize, if you transform your features, looking at all the data, you're getting